Well, hey guys, welcome back to the start of a brand new build series. Now, it all started out with a pretty simple project in mind, but as a lot of these projects tend to do, it spiraled out into needing a lot of prep work to be done first before I can do the project that I have in mind. The goal is sort of simple. I want to do a bit of modification to the spindle of the mill. It's a project I've been meaning to do for a long time, and on face value, it doesn't seem to be too difficult. The goal is simply to do a bit of milling and drilling on the spindle itself. However, in order to do that, I do need to remove the spindle from the mill's head, which means I obviously won't be able to use the mill itself to do any of the drilling or the milling. Now, to some extent, I could probably use the drill press, at least for the drilling, but I do want to index this part several times, and I do want it to be pretty accurate and precise work, so the drill press probably isn't the tool that I want to use. I'll also have to do a bit of milling, and since the drill press doesn't have a drawbar, I won't be able to use it to do any of the milling work. And that's where this project comes in. I'm going to be making a vertical milling attachment which will bolt onto the cross slide. It'll have a motor and spindle so I can do any drilling and milling work that I need to do. If it sounds like a bit of a crazy idea, it really isn't. These things have been around for ages, they're good pieces of kit, they're just not as good as owning a dedicated mill. However, with the mill out of contention, this is probably the best way to go forward. Plus, with the lathe now set up with T-slots, this is the perfect time to test it out. You know, this is the exact reason why I added T-slots to the lathe in the first place, and, you know, if I have them, I might as well use them. Now, to power this thing, I'm going to go down the click spring route of doing things, and I'll simply nick the Sherline spindle and motor off my lathe. It's a half decent combo, and the Sherline spindle is pretty well made, so it's a no-brainer to use it here. The motor's certainly on the smaller side, but the good thing about using it here is that it seems to work really well at low RPM. The fact that it has a step-down pulley belt probably helps a lot in that department. The last time that I did something similar to this, I used one of those router spindle motor combos, and that motor really struggled below about 6,000 RPM, and 6,000 RPM is still way too high for the type of machining that I need to do here. Now, unlike the cross slide, which uses dovetails, I'm instead going to opt for a linear rail. I can bolt the spindle to it, and that'll allow it to move it upwards and downwards. Using them here is pretty much a no-brainer. You know, they work really well, they're pretty well made. I have quite a few of them spare from a lot of old CNC projects that I used to do, and I don't have to worry about making gib strips or matching dovetails. Now, as for the construction of the frame itself, whilst you would probably want to use cast iron if you were wanting to use this quite a lot, because I'm simply throwing this together for a quick project, I'm simply going to use some plate steel, which I have lying around from an old project. I think it's roughly 1/2 inch by 3 inches, and whilst it's probably not the best material and the best shape, I can definitely work with it and get something very useful out of it. So the first thing I'll do is I'll get the pieces for the frame cut. I'll need 3 pieces, one for the base, one for the front, and a piece to support the back. So with all the pieces now cut, this is roughly what I'm aiming to achieve. It's not quite an I-beam, but you get what I'm getting at. This rib on the back should make it a lot more rigid. Now, normally from here, I'd fly cut all of these pieces flat, and I will do it for one of them, but for these long, thin pieces, I don't think I currently have a setup which would allow me to fly cut these and get them as flat as I would normally like. At times like this, it would be very nice to have 2 matched vices, so I could hold each end in a vise, but I don't currently have that. Instead, what I'm going to do is just leave them as is. I've checked and these pieces are mostly flat, so they should be okay for mostly drilling and a bit of mill work. And for a quick one-off project like I'm trying to do, these should be just fine. So the first thing I'll do is I'll get all the pieces in the mill and square up and clean up each end. Now this small part here is going to be for the base, so it's going to need 2 holes so I can bolt it to the lathe's cross slide. As always, it's pretty difficult to beat a fly cut finish. I'll then get the front plate in and I'll drill the holes for the linear rail. Now the linear rail is a little bit too long, so I will need to cut it down. And because the rails are hardened, I'll have to use the angle grinder to cut it down. Of course, nothing ever turns out to be as straightforward as it should be. These holes, which are sized for M6, don't actually take M6 caphead screws. For some reason, they've just made them a little bit undersized. Why? Who knows? So I'll take them over to the lathe and take down the diameter of the head by about 0.5 mm. Alright, and that's the linear rail now bolted in place. What I now need to do is add a mounting block onto the linear rail. This will be for mounting both the Sherline spindle and the lead screw nut. Again, I'll make this from a piece of offcut from a previous project. The first thing I'll do is I'll clean it up with the fly cutter, and then I'll get the holes drilled for the bolt pattern. The next thing that I'll do is I'll add a keyway to the block. This will match up with a keyway that's located on the underside of the Sherline spindle. Now the Sherline uses a 3/16 of an inch key, roughly 4.7 mm, and the way that I'll be cutting it is to use a 3mm carbide end mill, and I'll widen up the slot until the keyway snugly fits. Now I'm going to take this slowly because this is a $30 end mill, and the last thing that I want to do is break it the first time that I use it. Alright, and that's a pretty good fit. The next thing that I need to do is drill a hole for a stud. Now I haven't mentioned it yet, but the Sherline system uses a bit of a strange, or at least more unique style of holding the spindle into position. It uses a stud with an angled cutout in the middle, and a locking screw to push against that angle. If done correctly, that'll hold the spindle in place. Kind of a weird system, but it does work. However, it does require everything to be pretty accurately made, which is why I'm going to be reaming that hole. I'll then flip the part over and then counterbore the hole which we just made. And I'll make it big enough for a nut and a socket. With that now done, I'll start to make the locking stud. Now, because the Sherline is designed and made in America, everything about it is Imperial. And all the dimensions that I need to hit for the stud are all in Imperial. Thankfully, the DRO should make my life a little bit easier. So now that I've taken the first pass, I'll take a measurement using my metric calipers, and then I'll enter it into the DRO. I can then switch it to Imperial and then do all the machining with it in Imperial. Obviously it's not impossible to convert all the Imperial measurements into metric, but doing it this way is just a lot easier. Alright, and that's the block now done. And thankfully it is being held in place really tightly. I'm always really surprised with just how well this setup seems to work. All in all, really happy so far. With all that now done, we now need to think about how to advance the spindle and the linear rail. Most spindles use some sort of rack and pinion, which is what you'd want if you want a fast action, but it's usually a lot less precise. What I'll instead be using is a lead screw. Now I was thinking about making my own lead screw from scratch. Obviously I've done that a few times here on the channel, but given the nature of this project, it really isn't worth doing. Instead, what I'm going to use is some M16 threaded rod, which I have left over from a previous project. It's M16 by 2, so the pitch is a little bit finer than what I'd want, but it is still perfectly usable. It's not going to be as good as a purpose-built Acme thread lead screw. There's going to be a bit more resistance, but let's not overthink things here. This should work out just fine. I also have an M16 coupler nut on hand, so my fingers are crossed that I can modify this to make it work. So the first thing I'll do is I'll take 2 pieces of steel and I'll use these to make the bearing blocks for each end. This will be used to hold the lead screw in place. If you really wanted to, you could put bearings in them, but for a project like this, keeping them plain and just having a bit of oil for lubrication should be just fine. So with the blocks now machined to match, I'll take one of them and drill a hole all the way through. I'll then ream it for 10mm. I'll then drill and counterbore 2 holes, and this will be for mounting them to the front plate. I'll then swap it out and do the exact same thing on the second one. I'll then get the mounting plate in and then drill and tap 4 holes for mounting the bearing blocks. With that now done, I can now measure the exact length of the lead screw which I need to cut. One end's going to be really short, and this will be solely to go into the bearing block. The other end's going to be a lot longer, and this will go into the bearing block, but also accept a hand wheel. Alright, looking pretty good so far. We now need to get the coupler nut fixed in place. Now because I'm using an off-the-shelf coupler nut, there is a fair amount of backlash in this screw, so as well as trying to mount it, we also need a way to reduce that backlash. The first thing I'll do is I'll cut off a piece of steel and clean it up. This will be for a bracket which will attach the coupler nut to that mounting block. Now the coupler nut itself needs a fair amount of material taken off it. This first side is being taken down because it was a little bit too wide and it was hitting the linear rail. The second side is going to be taken down for the anti-backlash mechanism. I'll then sand it down to remove some of that galvanizing. Now this piece here is going to be for the anti-backlash screw. Now to make the anti-backlash bit work, I need to cut most of the way through using a hacksaw. I'm relying on using a screw to compress that gap, and in doing so, it's going to compress and hold onto the lead screw. Now that should reduce the backlash, but I can also use it as a lock. And given that I am using linear rails, you do need some sort of mechanism to act as a slide lock. And thankfully, that's working pretty well. And with all that now in place, that is working really well. Now the final thing that I need to do is get this thing assembled and welded in place. Now I need to be really careful with how I do this because welding is going to warp it, at least in some way. So I'm going to try and do minimal weld beads, and I'll have to constantly check it just to make sure that everything remains square. Alright, and that is the vertical mill attachment now connected to the cross slide. And I could not be happier about it. This is really what I designed the new cross slide to be able to do, and just to be able to see in action makes me really happy. It's not impossible to do with the old cross slide, but it would be a lot more difficult, and I probably wouldn't have done it. Doing it this way, I mean, it is just meant to be. Obviously I can't show you how well it works yet because we still aren't done. I still need to figure out how I'm going to hold it on the lathe, how I'm going to index it, and how I'm going to hold the tools. Anyway, I think the hard part is over, although we'll just have to wait and see. And with that, thank you very much for watching. I hope you enjoyed this video, and I'll see you next time.